All right, now in this example, we are told that squids and octopuses propel themselves by expelling water. They do this by keeping water in a cavity and then suddenly contracting the cavity to force out the water through an opening. A 6.5 kilogram squid, so let's start there. We've got that the mass, and let me hold off on putting a little s there because it says a 6.5 kilogram squid, including the water in the cavity, at rest suddenly sees a dangerous predator. So they don't actually tell us the mass of the squid, even though they kind of word it that way. They tell us that the mass of the squid and the water inside of the squid is 6.5 kilograms. So be careful how they word these. Okay. It asks if the squid has 1.75 kilograms of water. So let me put that down. The mass of the water all by itself is 1.75 kilograms. At what speed must it expel the water to suddenly achieve a speed of 2.5 meters per second to escape the predator? So we're told that we want the velocity of the squid finally, so not to start with, but when it gets scared, to be 2.5 meters per second. And we want to know how fast the water needs to be. Velocity of the water. Question mark. Okay. So the thing to realize with this problem, especially because it does say ignore any drag effects of the water, and so we just have the mass of the squid in the water just, suspended in water. And so since there's no outside forces acting on this system, momentum is going to be conserved. So remember that means that the momentum we start with, initial momentum, and momentum is represented with a P, that's going to equal the momentum we end with, the final momentum. And further recall that momentum is just the mass of whatever we're talking about times the initial velocity, and that has to be equal to the mass of whatever we're talking about times the final velocity. And if you have multiple things in the system, you would just account for all these things in that system at the beginning and at the end. So let's do this. So the thing is that it says that a 6.5 kilogram squid, including the water, at rest suddenly sees a predator. So to start with, the squid is just there. It's just floating in the water, not doing anything. In other words, the initial velocity is 0. So if we go back to the momentum form, we just say that the initial momentum is the mass of the squid and the water inside the squid times the initial velocity. Well, if the initial velocity is 0, this whole thing is going to be 0, right? Some mass, I could plug in numbers here, but it's this amount of mass times 0. That's 0. So that has to be equal to the momentum later. Well, what's the momentum later? Well, to start with, like we said, the squid is just floating there, and then suddenly, as the squid's floating here, a predator comes along, and the squid freaks out, and it shoots off this way. Now, when it does this, we've got our little squid here, which is essentially like a rocket ship. So I'll sort of draw it like that, but with an eyeball. When it does that, this arrow is representing the water it's pushing. So it's literally pushing the water this way, and the water is pushing back on it this way. And so we have the momentum of the squid is directed this way, and we have the momentum of the water that the squid just shot out of its tummy. It's not really its tummy, but its little water sac in here that it shot out this way is going this way. So that's the momentum of the water. So that's why I have positive momentum on the squid and negative momentum on the water, because they're going opposite directions. So now if we look at this, we have this equation right here, the final momentum is equal to 0. So we can just add things on both sides, solve this like we would any other equation. Now it's asking for the velocity of the water. So what I'll do is I'll go ahead and copy this down over here. 0 equals mass of the squid velocity of the squid minus mass of the water, velocity of the water. This is the negative term, so I'll add it to both sides. And so we get that the mass of the water times the velocity of the water equals the mass of the squid times the velocity of the squid. And then to get the velocity of the water by itself, we'll just divide both sides by the mass of the water. Fume, fume. And so we get that the velocity of the water is going to be equal to mass of squid, velocity of squid, over mass of water. And so at this point, we just have to plug our numbers in. And you might notice now that we don't have the mass of the squid by itself. But that's okay, because we've got that the mass of the squid plus the mass of the water equals this, and we've got the mass of the water right there. So let me use a different color, because I'm getting a lot of stuff up here. We have mass of the squid plus 1.75 kilograms is equal to 6.5 kilograms. Okay, well, to get the mass of the squid, just subtract 1.75 from both sides. So the mass of the squid, you can throw it in your calculator, or if you're amazing at doing stuff in your head, feel free. That's going to be 4.75 kilograms. So that's not what they asked. That's just the mass of the squid, but we needed to know that to actually solve this right here. So we're told the velocity of the squid. It needs to be 2.5 meters per second. That's what we're using. That's if the squid is going that fast, how fast must it shoot out the water? That's our relative frame of reference. So we've got mass of the squid. We've got mass of the water. Ooh, that looks like mass of squid. It's supposed to be mass of water. Bam. So let's plug all this in. The velocity of the water is going to be 4.75 kilograms, that's the mass of the squid, times the desired velocity of the squid, 2.5 meters per second, all divided by mass of the water, which was given, 1.75 kilograms. Notice here that kilograms cancel out, and we're just left with meters per second. So if you multiply 4.75 by 2.5 and then divide by 1.75, you should get approximately 6.79 meters per second. So just to recap, it was really helpful here that the squid was not moving to start with, because that meant that the initial momentum was 0. And so it meant that the momentum we're trying to solve, pieces of later, you can just move something over to one side and divide by what you don't want and carry on from there. So it greatly simplified the problem. So watch for stuff like that when you read these physics problems. They're always going to put it in very, almost casual speak, and you have to come up with the mathematical notation or what they're meaning by that. Notice the word momentum was nowhere in that problem description. So you have to realize, ooh, no drag force of the water, no outside forces. Momentum's conserved. The squid was at rest to start with. Momentum was initially 0. Ah, that means the momentum later has to be 0. Cool. If the squid shoots out water this way to go that way, they're in opposing directions, so you just set up the equation like that and then solve for whatever they ask for. So there you go. If the squid wants to go 2.5 meters per second, it's got to shoot that water out at 6.79 meters per second. And that is this example.